and good morning everyone. In the previous lecture, we studied about the design of the heel slab. In this lecture, I will be going to discuss the design of the stem portion of the counterfort retaining wall. Now, in order to design the stem, we must know its behavior. So let's discuss its behavior. That what is the behavior of the stem when earth pressure acts on the stem. So this is the earth pressure which is acting on the stem. When the earth pressure acts on the stem deforms in two directions, one in this direction and one is this direction. Suppose this is your x-axis, this is your y-axis, and this is your z-axis. So the deformation in the stem portion, it occurs in the z direction and the y direction. So we can say that the deformation in the stem is bidirectional, and hence the stem, it behaves as a two-way slab. Now if you see the stem along the z direction, you will find that the stem is fixed at the base and it is free at the top. It means the stem, it behaves as a cantilever structure along the z direction, and hence the cantilever action prevents, or you can say that it resists the deformation which happens in the z direction. Now if you see the stem in the y direction, the stem can be assumed to be composed of several strips of 1 meter width. Now if you see a single strip, you will find that each strip, these are fixed at both the ends. So we can say that each strip of the stem, it behaves as a beam whose ends are fixed. Therefore, the beam action which is produced in these strips, it is responsible to resist the deformation in the y direction. Therefore, when we will design the stem, we will design the stem for two actions. One will be your cantilever action and one will be your beam action. So now we will see that how we analyze the stem for the cantilever action and for the beam action. So first we need to see that what forces are acting on the stem. So there is only one force which acts on the stem apart from its self weight, which is soil pressure. So the soil pressure acts on the stem, and we know that the soil pressure distribution diagram is a triangular distribution, which is like this. Zero value at the top and it is maximum at the base of the retaining wall, and at the base the value will be Ka gamma h, where Ka is the coefficient of active earth pressure, gamma is the unit weight of soil, and h is the total height of the retaining wall. After putting all the values, I will get the value at the base of the retaining wall to be 53.295 kilonewton per meter width. Now, if suppose I want to find out the value of pressure intensity at the level of the bottom of the stem, see, we already calculated the thickness of the heel slab in the previous sections as 0.6 meters. If this is 0.6 meter, the height of the stem will be 9.5 minus 0.6 meters, that is 8.9 meters. Therefore, the value of pressure at this level will be 8 point Ka gamma h, that is 0.33 into 17 into 8.9, you will get 49.93 kilonewton per meter width. Now we will use this pressure distribution diagram to calculate the values of the loads and hence the values of the maximum bending moment and the shear force. So first of all, we will analyze our stem for the cantilever action. So one thing you need to know is that the lower part of the stem exhibits cantilever action. Cantilever action is more prominent near the lower part of the stem. Now we need to see that how much load will contribute to the cantilever action. So in order to find the load which will contribute to the cantilever action, draw yield lines at an angle of 45 degrees. So if you draw a line at an angle of 45 degrees from here and here, they will coincide at a height of 2 meters. It is basic trigonometry or basic geometry. So since this is an isosceles triangle, therefore this height and this base will be 2 meters. We can calculate it by basic geometry. Now this strip of width 2 meters, the load which is coming on this strip will contribute to the bending moment and shear force in the cantilever action. So we will now consider this. See this strip from the bottom of the stem. The width of the strip is 2 meters. So so whatever be the load coming on this strip of the stem, this load will contribute to the bending moment and shear force in the cantilever action. So now we need to find out that how much force is acting on this strip. So we will just draw the pressure distribution which we got in the above diagram. So we copied this diagram here. So the value is 0 here, and at the base of this stem the value is 49.93. So this is 49.93. See, if you see this diagram, and this is the elevation of the retaining wall. If I look from this side, so this is the elevation of the retaining wall. Now this is your heel slab. These two are the counterforts, and this is the stem. So the pressure distribution is this, and the load which will contribute to the cantilever action will be the load which will act on this strip of 2 meter height. So this total height is 8.9 meters and this height is 2 meters. Therefore, this height will be 6.9 meters, and the value of the pressure intensity at this level, at a level of 6.9 meters from the top, will be Ka gamma h, and the value of h will be 6.9. Just put the values here. You will get 38.71 kilonewton per meter width. See, now in order to calculate the bending moment, we first calculate the average bending moment, and from the average bending moment we then calculate the maximum bending moment. See, we are going to follow the same procedure which we followed during the design of the heel slab, because the behavior of the stem is same as that of the heel slab. So therefore, see, if you want to find out the average bending moment, now we know that this much load will contribute to the cantilever action, and the maximum bending moment, we know that in a cantilever structure the maximum bending moment is at the fixed end. So therefore the maximum bending moment will be at CD. So now we will calculate the moment due to these forces along CD. So first of all we will calculate the average bending moment of ABCD about CD. So if you see this diagram, this diagram is composed of two shapes. One is your rectangular shape and the other is a triangular shape. So now if I do the summation of the rectangular force and the triangle force and then take the moment of both the forces, I will get the average bending moment. So if you see this triangular portion, the area of the triangular portion is length into width. So the length is 38.71 and the width is 2. So this is your force, 38.71 into 2, and this force will act at the CG of the rectangle, and the CG of the rectangle is at acts at height by 2. So the perpendicular distance of this force from CD will be 2 by 2. So this is your perpendicular distance. Now if you see this triangle, so just take the area of this triangle, it will be converted into force. So half base into height. Base we can just calculate from the geometry. This is 38.71, this is total is 49.93, so the base will be 49.93 minus 38.71, that is 11.22. So this force will act at the CG of the triangle, and the CG of the triangle from the base is 1 by 3 of the height. So 1 by 3, and the height of the triangle is 2. So the perpendicular distance will be 2 by 3. So after calculation, I will get the value of M average to be 84.9 kilonewton meter. Therefore, M max will be 2 into M average, that is 169.8 kilonewton meter. Therefore, maximum moment per meter run. See, in the design of the counterfort retaining wall or a simple cantilever retaining wall, we design each and every component for per meter run. Therefore, we need to find out the maximum bending moment for per meter run of the stem. See, this bending moment which we just calculated, we calculated for 4 meter length. Therefore, for per meter length, it will be divided by 4. So the maximum bending moment per meter run will be 42.45 kilonewton meter. Therefore, ultimate moment will be 1.5 into M max. Factor of safety, just multiply M max with factor of safety. So therefore, M ultimate will be 63.68 kilonewton meter per meter run. Now we will calculate the value of PT for this for the bending moment. So we know the formula of PT. So after putting the value of PT of all the variables here, we will get the value of PT as 0.06 percentage. And see one thing, in this formula we have used small d. Small d is the effective depth, and the formula for the effective depth is total depth minus nominal cover minus pi by 2. And we have assumed that we are providing 20 mm dia bars, therefore the dia will be 20. And we have also assumed that the nominal cover is 50 mm, therefore the value of the effective depth will be 540 mm. So that's why we have put here 540. So after putting the value of the area of the percentage of steel PT is coming out to be 0.06%. Now, we will calculate shear force at CD. We know that shear force in a cantilever structure is also maximum at the support, that is this base of the stem. Therefore, we will calculate shear force at CD. So shear force is the summation of forces. So just take the summation of forces of this rectangular portion and this triangular portion, and we convert these portions into force by taking just the area of these shapes. So there are two shapes, rectangular and triangular. So average shear force will be equal to area of rectangle plus area of the triangle. So these will be converted into force. So total shear force, average shear force will be 116.13. A similar way, Vmax will be 2 times V average, then Vmax per meter run will be divided by 4, and then we will calculate the value of ultimate shear force, which will be factor of safety into Vmax, and the value will come out to be 87.10 kilonewton per meter kilonewton per meter run. Now, with the help of this VU, ultimate shear force, we will now find out the value of tau V, which is VU upon VD. See, the value has come in kilonewton. So in this formula, we will convert it into Newton so that it can be converted. So that the value of tau V comes in Newton per mm square, that is MPa. So we will take every unit in Newton and mm. So VU will be into 1000 newtons. Width is 1 meter width because we design for 1 meter width. So 1 meter is 1000 mm. D we already calculated, the value is 540. So the value of tau V will come out to be 0.16 MPa. Now from table 19 of IS 456, we will take tau C equal to tau V equal to 0.16 MPa, and if you will see in the table 19 of IS 456, you will find that for 0.16 MPa the value of PT is not given. Okay, for 0.25 or 0.28 it is given. So this value is less than that value, but the area of steel cannot be less than percentage of steel cannot be less than 0.12 percentage. Therefore, we will take the minimum reinforcement, that is 0.12 percentage. Now we calculated the percentage of reinforcement for MU as 0.06 percentage, but we require 0.12 percentage of steel to resist the shear force. Therefore, we will provide the maximum of these two values, and the maximum of these two values is 0.12 percentage. Therefore, we will provide the larger value. After putting the formula PT equal to AST upon BD into 100, we will find out the value of AST, which will come out to be 648 mm square. So this is the amount of reinforcement which we will be going to provide for the cantilever action. And if you want to find out the spacing, just use the formula equal to here I have not calculated. Spacing can be calculated by area of one bar into 1000, this divided by total AST. So from here you can find out the total spacing. And if spacing, see, one thing you should remember, that spacing should not be greater than 300 mm. So if spacing comes out to be 400 mm, you will not take 400 mm, you will take 300 mm. So this was the design for the cantilever action. Now I will proceed to the beam action design. So we know that the beam action takes place along the y-axis, that is along this direction. And for beam action we divide the stem into strips, small strips of 1 meter. See now, one thing comes that which strip do we have to take? Do we have to take a strip at the top of the stem, or do we have to take the strip at the bottom of the strip, or do we have to take the strip at the middle of the stem? See, if you take the strip at the top, uh, the value of the pressure intensity at the top is minimum. And if you take the strip at in between, the value, see, if you go from top to bottom, the value of the pressure increases. So it is obvious if we take the strip at the bottom, the value maximum pressure intensity will be considered. So if I take the strip at the bottommost portion of the stem, the pressure intensity will be maximum. And if I will use the maximum intensity, I will get the maximum bending moment. And in every design, we have to design every component for maximum bending moment. So we can get the maximum bending moment only by putting the maximum value of the load. And the maximum value of the load is at the bottom of the stem. Therefore, we will consider 1 meter wide strip at the base of the stem. So here we have considered a strip of 1 meter width. So if this is 1 meter, this will be 7.9 meter, and hence the value of pressure at this level will be Ka into gamma h, that is 0.33 into 17 into 7.9, which will give you 44.32 kilonewton per meter 1. Therefore, average loading on the strip. See, if you see this strip at the top, the value of the pressure intensity is something different, and at the bottom it is something else. So we will take the average of the two values. After taking the average, it will give you W average. So after W average, I can find out the value of ultimate load, which will be factor of safety into W average. So this will give you 70.69 kilonewton per meter. Therefore, the negative bending moment, which we see the same formula which we used in the design of the heel slab, we will be going to use the same formula here also. In this formula, if you want to revise it, I can explain you again. If you see this beam is fixed at both the ends, and if the beam is fixed at both the ends, maximum negative bending moment occurs at the supports, and its value is WL square by 12, and the maximum positive bending moment occurs at the center of the span, which is WL square by 16. So therefore, maximum negative bending moment will be WL effective square by 12. Put the value of WL effective we already calculated during the design of the heel slab, which was 4.54. After putting the values, I will get the value of mu negative and mu positive. Now we will provide the reinforcement for mu negative. So just find out PT equal to this from this formula, put the values. We will get PT equal to 0.12 percentage. Now we will check the reinforcement required for the shear force also. So shear force, we know that in the beam action, its formula is WL by 2 minus D. Now how we got this formula, I discussed in the previous video of the design of heel slab. So by putting this formula, you will get the value 122.29 kilonewton. So from this value, I can find out the value of tau V, that is VU upon BD, convert this into Newton by multiplying it with 1000, this divided by B into D, so we will get 0.23 MPa. Now from table number of 19, IS 456, put for tau C, take tau C equal to tau V equal to 0.23 MPa. So for 2.23 MPa, the value of PT from this table will come out to be 0.12 percentage. See, now for mu negative, the percentage is coming to be 0.12, and for VU also the percentage is coming out to be 0.12 percentage. So both the values are same, therefore we will take PT equal to 0.12 percentage, which is also equal to the minimum steel required. So therefore AST will be equal to, from this formula, what we are using already. So from this formula, the area of steel will come out to be 648 mm square. In the beginning, we assume that we are providing 20 mm dia bars. Therefore, the spacing will be area of 1 bar into 1000. This divided by AST. Area of 1 bar will be pi by 4 into 20 whole square into 1000. This divided by 648 will give you 484 mm. But the maximum spacing is 300 mm, which I already told you. So therefore, provide 20 dia at the rate 300 center to center. See, Now we have to provide the reinforcement for the positive bending moment. So if we see above in the calculations, you can see that the value of the positive bending moment is coming out to be less than the value of the negative bending moment. Therefore, the area of steel required for positive bending moment will obviously be less than the negative bending moment. But for negative bending moment, we have provided minimum reinforcement. So we cannot go below 0.12 percentage. Therefore, we will keep it as 0.12 percentage only for Mu positive also. So therefore, take PT equal to 0.12 percentage. Now for put the value in this formula, you will get the value of AST as 648 mm square. See, now the value 648 which we got for the positive bending moment. Now this value, this reinforcement is decreased as we go above the along the height of the retaining wall. So as we go above the height along the height of the retaining wall, along the height of the stem, the reinforcement is reduced after every h by 3 height. So if the reinforcement at the bottom is 648, it will get reduced by some amount for this much height for the next h by 3, and for the next h by 3 this reinforcement will again get reduced. So now we have to find that what exactly be the amount of reinforcement which we will provide for each h by 3 zone of the stem. So for this, I have explained you something. See, suppose the effective depth for the total height h is small d. Therefore, for a height of 2h by 3 from the top, the effective depth will be d by h into 2h by 3. See, I'm just using unitary method. So if for h the effective depth is d, therefore for 2h by 3 from the top, it will be d by h into 2h by 3, that is 2 by 3 into d. And similarly, if I will take 2h by 3 from the bottom, the height from the top will be h by 3, h by 3 from the top. So since same thing, if the effective depth for h is d, therefore for h by 3 from the top, the effective depth will be d by h into h by 3, which will be 1 by 3 of d. So we will be using these values for the calculation of AST in each zone, zone 1, zone 2 and zone 3. See, we know that AST is equal to 0.12% of the cross-sectional area. So therefore for D1, AST1 will be this. If I divide both the equations, equation 2 by equation number 1, I will get AST1 by AST equal to D1 upon D. So I will get the formula of new AST as D1 upon D into AST. Now, if I want to calculate the area of steel in this zone, zone 2, so zone 2 is at a height of h by 3 from the bottom. So h by 3 from the bottom, the value of d1 is 2 by 3d. So just put 2 by 3d, original is d, into original is 648. So the area of reinforcement in the second zone will be 432 mm square. Now, if you want to find out the area of reinforcement in the third zone, that is whose height is 2h by 3 from the bottom, the value of d will be 1 by 3d. So just put the value of d1 as 1 by 3 of d, original is d, into original area 648, so we will get the value as 216 mm square. So this is the design of the stem portion of the cantilever of the counterfort retaining wall. Now in the next lecture we will be going to study the design of the counterfort of the counterfort retaining wall.